have if for an abelian variety is a principally polarized abelian variety such that there exist points z1, z2, z3 inside the abelian variety such that twice zi is not 0 for any zi. I'm trying to be more precise to say this are non-singular points of the Kuma variety, and zi is not equal to to plus or minus zj, zj, such that the Kuma image of z1, Kuma image of z2, and Kuma image of z3 are linearly dependent, then the principally polarized abelian variety is a Jacobian. Okay, so that's the theorem. And you were suggesting.
So I just wonder whether you can reduce this theorem to the Guyhnic theorem you mentioned previously.
So this is a very high dimensional condition, right? So this is a condition for 3 points in a 2 to the g dimensional space to lie on a line. And in Guyhnic theorem, you are saying, you're saying if you have a Jacobian, right, then on a Jacobian there is a 4-dimensional family of trisecant lines.
In 1 dimension?
Well, on the Jacobian there is a 4-dimensional, because on the Jacobian, remember, you can choose P, Q, R, S in the curve. So there is a 4-dimensional family of trisecants for a Jacobian.
Yeah, so I mean, the formula for the Kuma map,
right,
have this PQRS.
Right, and there are some expressions of the type like this. Yeah. Yeah.
What I'm wondering is if you can find 3 points on G3, which can be expressed in terms of PQRS, then for given G1, G2, G3, you can allow this PQRS to vary.
So you see, I understand. So the question, if I think now I understand it, is as follows. So there was a separate theorem due to Guyhnic. Let me try to reformulate it in a way that will make it look similar to this. So the theorem due to Guyhnic, well, was the following. If A theta is a principally polarized abelian variety such that there exists a 1-dimensional family of P such as there exists and 3 points z1, z2, z3 in the abelian variety such that the Kuma images of P plus z1, P plus z2, and P plus z3 are collinear for these fixed choices of z1, z2, and z3, and for this variable P, then your abelian variety, your principally polarized abelian variety, is a Jacobian. This is Guyhnic theorem. You notice this is not just saying that there is a 1-dimensional family of trisecants. This is saying that there is a 1-dimensional family of trisecants that are sort of all translates of each other. Translates in the sense they go through 3 points and through translates of these 3 points. So what you were saying was the following, that if I look at a Jacobian, then there are PQRS which somehow enter each of the 3 things. But you cannot solve back for PQRS from these 3 points because this is 3 points on C to the G. And PQRS are on the curve. Does this make sense? Yeah, okay. So, but I'm glad that this gave me a chance to write Guyhnic theorem in this form because I wanted to do it anyway. So that's very good. Okay? So that's somehow the end point of the previous talk. And now we'll sort of start an almost blank page. So I hope you will keep everything we discussed in mind. But now I'll start the analytic theory of the theta function. So the goal for the next hour is to introduce theta functions, theta constants, and tell you something about their properties. And then, depending on whether we have time, we'll start talking about differential equations either later today or tomorrow will be devoted to differential equations. More likely we won't have time. So theta functions. So of course this is the same theta function that eventually made its appearance in the talks before, but now I'll have a much more analytic view of it. So let's do a toy example first. And the toy example will be, well, it's not really so toy, it's elliptic curves. So suppose you have an elliptic curve, which is a quotient of z by z plus z tau, right? So you have an elliptic curve that looks like that. So there is 1 and there is tau, right? And suppose you wanted to understand the following question, which is the following. What do all the meromorphic functions on the elliptic curve, let's denote it E, look like? Okay? So what does this mean? So if we have a meromorphic function, if we know where its zeros are with multiplicities, and we know where its poles are, of course we know what the function is up to a constant scalar. So up to a constant factor, a function, a meromorphic function, which I'll write as a map to P1, is the same as its zeros and poles. Okay? So this means all we have to describe is we have to describe the sets of zeros and poles that meromorphic functions can have in principle. So what do we know about zeros and poles from complex analysis courses? Well, depending on which complex analysis course you went to, it could be different, but hopefully one thing you may know is that the number of zeros is equal to the number of poles. Right? So how do you prove this? Well, there is one sort of topological way you can see this. You can say with multiplicity. You say, well, this is a map from an elliptic curve to P1. This map has a degree. The degree is the number of pre-images of any point. And it has to be independent of the point. So the number of zeros is the number of pre-images of zeros. The number of poles is the number of pre-images of infinity. That's one way, but this is not necessarily the way I'd like to do it. Another way you can do is you can integrate something like, okay, now I will always make a mistake, so it's either, so if I take the integral over, so I want to integrate over the boundary sort of the Riemann surface, so I want to integrate dz, I think, over, I want to integrate d log z, right? Then I would, so what kind of a, d log, sorry, f of z. Yeah, so I want to integrate that. Okay, so on one hand this has to be 0, you would think, but on the other hand this will count the number of poles, number of zeros minus number of poles. Okay, is this correct or did I do something wrong? So if function f so let's see. So I want to count the number of zeros. So whenever f is 0, this will have a pole. And if it is 0, so if f is locally like z to the k, right, log f is locally like k log z. And then this means d log f is locally like k dz over z. Okay, so this seems correct. Maybe I forgot an I over 2 pi or something like that here. Okay, that's one thing you can do. On the other hand, so let's say that, say, the divisor of f, so the set of its zeros and poles, is equal to the sum of ni pi, right? Where this includes zeros and poles. So we know that the sum of ni is 0, but on the other hand, there is a theorem which is called Abel Serum. That's 1/2 of it, which is to say that the sum of ni pi is 0 inside the I think of this as an element of the elliptic curve. Right? So the point pi is a point on an elliptic curve. I can add points, and I can consider this divisor, and I can just add points together. Right? And the way you get this is you integrate something like f d log f or some quantity of this sort. Or maybe you integrate z d log f, I think. Yeah, I think you need to integrate z d log f. That should work, because then you would pick up the value of each zero pole together with the multiplicity, right? And then you will see this is 0, and by the same argument, you would hopefully see that the sum of this sort is 0. Okay? And the full theorem is the following. The statement is, so the theorem, Abel theorem for partial, is the following. The set ni pi for ni in Z and pi in the elliptic curve is the divisor of some meromorphic function on E, if and only if the sum of ni is 0 and the sum of ni pi is 0 as an element of the elliptic curve. Okay, so this is the if and only if statement. Before, I argued that by integrating z d log f, you could get the statement that if you have a divisor of meromorphic functions, this will be satisfied. So now I'm saying that if these are satisfied, you can in fact construct such a meromorphic function. So this relates back to the original question of what do all the functions look like. So this is sort of an answer to this question, right? You just take a bunch of points satisfying these two conditions, and this gives you a meromorphic function up to a constant factor. So now the question you can ask is, well, how does one prove it? How does one construct such a function? And I'll now give you an answer which will not be the answer maybe the way it was originally thought of. So construction meromorphic functions. So recall we have this thing called theta function, theta of z, right? So it's a map from C to C, which is a section of theta on the elliptic curve, right? That's the polarization. I will write down a formula in a second, but I first want to show to you why this thing will appear. So if we have this, if we have such a thing, so it's a section of the theta bundle, how can we get from this something that will have a 0 at the prescribed point? Well, what does this mean? This means it's a section of the bundle theta. So in particular, the degree of the theta on an elliptic curve is 1. And in fact, the way I'll normalize things will be such that theta of z is 0 will be equivalent. So there is one point which is the principal polarization, and I'll choose this one point to be 1 plus 2 over half. So it will be the point in the center of the parallelogram here. I mean, that's the choice, okay? So then, if I were to choose any point A in the elliptic curve, for theta of z plus A plus 1/2 plus 1 plus t over 2 is 0, is equivalent to z equal to maybe minus a here, will be equivalent to z equal to a on the elliptic curve, right? Because this function has 1, 0, which is just to translate of this 0. This is 1 plus tau over 2. Okay. So this means we sort of have a function with 1, 0. It's not really a function. It's, of course, a section of a certain bundle. So then, for any ni pi satisfying Abel Serum, we will just write down an expression. We'll write f of z, and we'll just write the thing that we know will have the correct zeros and poles, and then we'll hope that it will be a function rather than a section of some bundle. So we'll write a product of theta functions of z minus pi plus 1 plus tau over 2 to the power ni. The product over all I, however many there were. So you see this thing has a 0 at the point pi. If ni is positive, then this power will have the 0 of corresponding order. Then if ni is negative, this will have a pole at the corresponding point of the corresponding order. Okay? So f is then a section of what bundle? Of the sum of all I of ni times theta shifted by minus pi plus 1 plus tau over 2. Right? Okay. So this means if we just add, this is the bundle, the sum over I ni theta, and this shift will be the sum over ni times pi, minus pi plus the sum of ni times 1 plus tau over 2. Right? That's the bundle. So I'm writing in this way, shifting a bundle. Okay? Maybe. But the sum of ni is 0. The sum of ni is 0, and this is also 0 as a point on the elliptic curve. So this is 0, which is to say is a trivial bundle. Okay. So this is an explicit construction of a meromorphic function on an elliptic curve with prescribed zeros and poles once I actually give for you the theta of z. Okay. And this theory generalizes well to higher genus. I'll say a word about that in a second. So let me now define the theta function, finally. So the theta function of tau and z, so I'll write it as a function of tau and z. So the tau was somehow implicit in all the discussion, but let me write it here to emphasize the dependence. So this will be, by definition, the sum over all integers n of the exponent of pi I n transpose, n squared tau plus 2 pi I n z. Okay. So this is a sum. Notice that the imaginary part of tau is positive, right? So this means this is I times something with positive imaginary part, so this will converge quite well because this will be exponent of something negative times n squared. Okay, and this will not matter much. Okay. So this is the definition of the theta function. So exercise, which I do highly recommend, is check that theta in fact gives a line bundle, gives a principal polarization on the elliptic curve E corresponding to tau. So what does this mean? It means this is a formula for a map from C to C, and you can verify that it satisfies correct orthomorphic properties, which is to say that theta of tau z plus n tau plus m is equal to some function, which will be some exponent, times theta of tau z for any z, any tau, and any integral n and m. Okay? So then it will be a section of a certain bundle. Then you need to find out what the degree is, and the degree will be 1. You can do this by integrating or in a variety of ways, or you can try to think about when this vanishes. Okay? So we note that theta is an even function. By definition, because if you change the sign of z here, you can also change the sum of n and the summation. So here the sign will not change then, and here the sign will not change. So this is useful, but you could recall that somehow when we were discussing polarization, we wanted to talk about symmetric polarizations, and there was more than one. So another possible choice would be to take the theta function and just to shift it by a point of order 2. So a shift theta of tau z plus point of order 2 would also be a reasonable choice. So points of order 2, again, there are 4 points of order 2 on the elliptic curve. Here they are. So there are 4 things. And so instead of writing this, so let me define the theta function with characteristic. And I'll define this in full generality, so characteristic epsilon and delta, which will be in Rg. Okay? So what this is going to be, and the notation is going to be as follows. So you write theta epsilon in R. Sorry, there is no G yet. And as you can see, I'm trying to set up in a way that will easily generalize to higher genus, but let's not get ahead of ourselves. 0 is a point of, it's a point of order 1. Right. But for this discussion, it's natural to include it in the set of all points of order 2. So there is always this delicate point of whether you consider the torus or the abelian variety and so on. So I would like to consider the points of order 2, for me, would not be the points such that if you add them to themselves, you get a 0. This is the fixed points of the involution. And that somehow is a better way to think about them. And then 0 is a fixed point of the involution like any other. Okay? So there are 4 of these things that you could consider. One of them, it turns out, is a little bit different, as we'll see in a second, but let me define it first. Okay? So this is going to be the following thing. So it's roughly going to be a shift of the theta function. But let me write down a formula first, and then we'll discuss what this is. So it's a sum over n in z of the following expression. Exponent. Let me write this in a new line so that I'll have space for going to higher dimension. So this will be the sum over n and z of the exponent of pi I n plus epsilon squared tau plus 2 pi I n plus epsilon z plus delta. So this is a definition. Of course, I can write pretty much any definition I like, but I'd like to know that this is some exponent, a reasonably easy one, times the theta function, the usual one, at z plus tau epsilon plus delta. So you can see z plus delta immediately in here, right? So if I were to erase delta from here, that's the same as adding delta in here by the definition of the theta function. Then tau epsilon, if I add tau epsilon here, I'll get a term which is tau epsilon squared, which is the same term I'm getting here. So it will be the same. And the exponent you can easily compute. It will not be important for what we do here. Okay. So for epsilon and delta being in 1/2 z over z, so this means they either 0 or 1/2, theta epsilon delta tau z gives a symmetric polarization on E, which is to say that its zero locus, which is 1 point, is going to be a point of order 2. But I don't want to write it because, I mean, well, maybe I should. Okay. So this is a definition of the theta functions in one variable. Let me briefly talk about generalizations, then we'll come back to the one variable case to understand more properties of these things first. So many variables. So now for a curve, sorry, let me take this back and let me see what's the right way to proceed now. No, I mean, let's not go to many variables first. Let's continue. Sorry. Okay. So we now have 4 these theta functions with different shifts, right? And you notice that if you take a square, so for any epsilon delta in 1/2 z over z, the square of the theta function with this characteristic is a section of 2 theta, because this exponent doesn't matter. It's a number essentially. I mean, it's not essentially just a number. So this means that you're talking about the theta function shifted by a point of order 2. So the square will kill the shift, and all of the squares will be sections of 2 theta. Okay. So I would like to then define a basis as promised, theta epsilon of 2 theta, which is going to be the following. So theta function of the second order are the following for any epsilon in 1/2 z over z. The theta epsilon of tau and z by definition will be the theta function with characteristic epsilon 0 of 2 tau 2z. Okay, and of course you can write down the exponential expression if you want. This is a very strange, maybe formula, maybe not so strange, but here is a proposition. So theta epsilon, and I mean we're in dimension 1, so there are only 2 choices here. It's either 0 or 1/2. Are a basis of z are a basis for sections of 2 theta. Okay. So I won't really prove this, for which I do apologize, but that's what they are. And you notice that there are a couple of things I would need to prove here. One thing I would need to prove is that they are actually sections of 2 theta, and this is what I would like to actually discuss. And then I would need to discuss that they are, in fact, a basis. And since there are 2, and I know this is a 2-dimensional space, all that is required will be to show that they are linearly independent. Showing that they are linearly independent will actually be very easy, but I don't want to do it. because you see there are these things, right? And these things are sections of different bundles on the abelian variety corresponding to 2 tau. So if there were a linear relation between this, there would be a linear relation between sections of different bundles on the abelian variety, on the elliptic curve with period 2 tau, and that's nonsense. But that's not the proof I want to do. So the important thing to remark, we need to understand why theta epsilon of z is in fact a section of 2 theta. Okay? Because somehow I wrote an arbitrary formula. Well, I mean, it wasn't an arbitrary formula really, but it was a formula. Okay? So let's try to understand this. So what happens? So we have our elliptic curve. Let me go up here. We have an elliptic curve here, right? And then I'm doing two things. I'm changing, so this was 1 and this was tau. I'm changing tau to 2 tau, and then I'm changing z to 2z, right? So this means I'll also have somewhere nearby the elliptic curve 1 and 2 tau, right, which is also an elliptic curve. On this elliptic curve, I certainly have its own theta function, right? But let's try to see what kind of a map I want to take. I want to take a map that takes z to 2z. What does this do? So if I do this, this means that this thing will get mapped onto a parallelogram of double the size, right? And then I sort of have to fold it back to one of the two copies. So you see, if I were to write the theta function of tau and 2z on one abelian variety, this is the pullback of theta tau z under the multiplication by 2 map, right? If I take an elliptic curve and I map it to itself by taking z to 2z, and I pull back the theta function, I'll get this, right? But this means that theta of tau and 2z will be a section of 4 theta, because the map, has degree 4. Okay, but since I'm going to taking 2 tau, it will only be a 2. Okay. So I mean, the issue is if you want to think of this analytically, there are 2 issues you have to think about. One issue is you have to think that you have to convince yourself that this is indeed a section of some line bundle in the abelian variety corresponding to tau, which is to say that if you add a vector n plus m and tau plus m, then it transforms corresponding. And then you have to convince yourself that it's degree 2, that it vanishes at 2 points. If you want to think of this algebraically, there is a certain isogeny that I'm writing here. I'm saying that the period matrix 1 tau can be mapped to the period. This one you can cut in half, essentially, which is the same as going the opposite way, right? So that's what happens. So you're pulling back the theta function under a certain isogeny, and you need to compute the degree of an isogeny. But let's not do that. Okay? So then Rimas by exercise is to prove Rimas by linear relations. Which, recall, is a statement that theta of x plus y, theta of x minus y is equal to the sum of theta epsilon of x, theta epsilon y. Okay. Now this is some identity that you can just prove by plugging in the formula. So all of this are some exponential Fourier series. Just plug in, you make sure they get equated term by term, and miraculously enough it will work. Okay. In particular, one example of this is if you just take a square of a theta function with characteristic. right? Because this is a section of 2 theta, so this is roughly the same as taking x and shifting it by tau epsilon plus delta, right? And if you do this carefully and you compute the corresponding shifts, what you'll get is you'll get the sum, and of course now I'll have to change the variable of summation, I apologize, and this will be minus 1 to the power 4 sigma dot delta, 4 sigma delta, sorry, theta sigma of x, theta sigma plus epsilon of 0. Right, because I mean, if you choose x and y to be x and 0, you get x for both of these. And then somehow the epsilon delta will correspond to, on one hand, the shift when you take the half sum, and on the other hand, it will correspond to this power of minus 1 when you use this property. Okay? So this is all an exercise. We won't need this particular formula. This one you can now check. Okay. So another question, so this is somehow the construction in genus 1. Another question you could ask is the following. So why choose theta of tau z, not say theta of tau z times some function of tau? Because you see, we didn't really have any normalization of the polarization. We could multiply the function theta by a factor of 2 just as easily on a given abelian variety, and then this factor could vary as we vary over the space of all abelian varieties. And there is nothing that would prevent us from doing that. Well, there are two answers. One answer is that in higher genus, this f would have to vanish somewhere, and that's not such a good idea because you don't want the polarization to vanish. But another answer is there is a proposition, which, I mean, that's an ad hoc answer. That's, I mean, I'm making a choice, right? So what I really have sort of to start with is I have a theta function on each elliptic curve. Why I have this nice formula for the theta function globally? It's that this is my choice of how I normalize it essentially on each abelian variety. This choice is justified by the following proposition, that if you take the theta function of tau and z, you can take its derivative with respect to tau. On the other hand, you can take its derivative with respect to z. And let's actually take the second derivative with respect to z. Let's look at this formula and see what happens. So if I differentiate with respect to tau, from each term, I'll get a term which will look like pi I n squared, which will come down in front. If I differentiate it with respect to z, from each term I'll get 2 pi I n. If I differentiate it twice with respect to z, I'll get 2 pi I n quantity squared. Right? So this means that here I can write a formula, and there is some appropriate multiple of pi I that I should put in the appropriate place. So I think it's 1 over 4 pi I here. Okay? And now you notice that if I were to multiply the theta function by f of tau for some f, this will no longer be the case. And this fixes f of tau to be a constant. Because if you were to multiply the theta function by f of tau, this sign will get multiplied by f of tau, but here you'll add the derivative of f of tau, which is impossible. Okay? And this is a very important property of the theta function, which is called the heat equation. And if you look at all the formulas I wrote here, this will also satisfy the heat equation in the same form. The theta functions of the second order will satisfy the heat equation, but with 1 over 4 pi I replaced by 1 over 2 pi I or 8 pi I or something like that. Okay. So this is the theory of the theta function in one variable. There is a bit more that we'll discuss shortly. So you notice we have discussed somehow the dependence on z. I never really touched upon the dependence on tau so much, and we'll do that briefly. But now, of course, the question is what happens in higher genera. And the theorem for Riemann surfaces is still Abel theorem, that there exists a function f from a Riemann surface x of genus G to P1 with prescribed divisor sum of ni pi, if and only if the two conditions hold, that the sum of ni is 0 and the sum of ni pi is 0 as a point in the Jacobian of the Riemann surface. Maybe I was denoting them C. Okay. Notice that if the sum of ni is 0, it doesn't matter whether I think of the Jacobian as peak naught, peak g minus 1 or something, because if I choose a base point to identify peak naught and peak g minus 1, it will get cancelled because of this condition, because they all will get shifted by exactly the same. Okay. So this is a theorem, and to prove this way is you can do by construction, and the construction will be again a product of theta functions of a certain kind. Okay. And it's a bit more delicate, because now a theta function will not have just one zero on the Riemann surface. It will have g zeros. So what you'll have to do is you'll have to prescribe g minus 1 of them to be the same for all of the factors, and then the last one you'll get to be the one you want, and then everything else will cancel. But I don't want to go there because it seems we won't need it so much. So this is a motivation for how theta functions in many variables will be useful. So let me now define a theta function in many variables. So I'll just go along the blackboard and I'll make the corrections, and I'll do it slowly enough so that you could sort of copy the general definition without making the correction in a notebook, which is impossible. So definition: for tau being in the Ziegel-Upper half space and for z being a vector in c to the g, the theta function of tau and z is going to be equal to the sum of all integral vectors in z to the g of the exponent. Well, we cannot write n squared tau anymore, but we can write n transpose tau n. So what does this mean? Tau is a matrix. It's a g by g matrix. This is a vector. This is a covector. You can take this product. It's a number. Here you also need to take a transpose, so they can take a scalar product of n and z essentially. Okay. So this is a definition, and then there is an exercise to check that this gives a principal polarization on the abelian variety corresponding to tau. Okay. Which means that you are supposed to check that if you add any lattice vector, then the theta function gets multiplied by a certain factor that you can control. Okay. The theta function will still be even. The reason it will be even will be, again, that if you change the sign of z, so you change the sign of all components of z, then if you change the sign of all components of n, this will not change, and this will not change. So the theta function will be an even function. Okay. Similarly, you could shift the theta function by a point of order 2 and get the correct, get a symmetric polarization. So then you can define a theta function with characteristic, which will now have to be g-dimensional real vectors. Okay, by writing in the same way as you were doing over there. Okay, and the sum has to go over g-dimensional integer vectors. And this is still equal to essentially the same, I mean, it's some exponent times the theta function of a shifted argument. Now each of this is a vector, and you just consider them to be vectors. So this is a matrix, a G by G matrix, which is multiplying a G-dimensional vector. Okay, and then for characteristics, you'll just need to choose vectors. The most interesting ones will be vectors of zeros and 1/2, and this will be a symmetric polarization on the abelian variety corresponding to tau. Okay, and it will vanish, on some divisor, so not just at one point of order 2. Okay. For any epsilon delta, the square of the theta function is still a section of the twice principal polarization on the corresponding abelian variety. And then if you wanted to construct a basis for the sections of 2 theta, you just take any epsilon and 1/2 z over z to the g's power, and you do exactly the same definition, and they form a basis of a space of sections of A. And the discussion we had over here about isogenies carries through. They are in fact sections of 2 theta. And Rimas' bilinear addition theorem holds as stated. So here you're supposed to take transpose, so this makes sense. So this is the definition of a theta function of many variables. And I realized that in a way it went by too quickly because we didn't really do anything new. We just somehow looked at these formulas and we tried to make sense of them for vector valued and matrix valued arguments. Okay, so you can again choose ask why not multiply by f of tau. One reason is it would vanish. If it does, this way it does not vanish identically, which I am not going to prove. You can also ask what happens to the heat equation. Well, now the period matrix has many components, so you have to choose which one you're going to differentiate with respect to. And the z also has many components, and if you say which one you're going to choose, well, you'll get something here. And now I'll have to correct this coefficient a little bit, so there'll be something a bit problematic. So it will be 1 over 2 pi I times 1 plus delta jk. So there is an extra 2 that appears if you are doing this with respect to a diagonal component, and there is no extra 2 if you are doing with respect to an off-diagonal component. It just comes out from this formula. If you carefully differentiate, you'll see that somehow tau jk for j not equal to k gets multiplied by nj and nk in two different, it appears twice here. Doesn't matter. Okay? Any questions on this definition? So I didn't do anything.
So what is tau jk?
So tau is a matrix now, right? So tau is a G by G complex matrix. So I just want to denote by jk its entry number jk. So this discussion is completely non-invariant now. We're actually, the theta function is defined here, so I'm numbering the coordinates, and I want to do that. Okay? Questions? Okay, so now let me briefly say a few words about the Schottky problem and so on. So let's get back to genus 1. So back to genus 1. So the question I want to study now is how does theta depend on tau, not on z. So I somehow motivated that the theta of tau z is the only natural choice if you want the heat equation, or in general, this gives you a non-vanishing polarization. Okay? How does theta depend on tau? So you see, I defined this thing, and you didn't object, luckily for me, as a function on Hg. I know, but somehow I should be getting some natural polarization on any abelian variety. So you can ask what happens. So what happens here, I'll try to write the general formulas for as long as I can. So we're going to do the general thing. So remember that the moduli space of principally polarized abelian varieties is the quotient of Hg by the action of the symplectic group, where for gamma equal to A, B, C, D in G by G block form, the action of gamma on tau is A tau plus B, C tau plus D inverse. In the other order. So, well, anyway, let me write it correctly. Okay. So in genus 1, these are numbers. In higher genus, this is a matrix I'm taking an inverse of. Okay. So proposition: there exists a certain finite index subgroup denoted gamma 48, and I really don't want to tell you what it is at this moment, inside SP2GZ, such that for any element in this subgroup, and for any tau in the Ziegel upper half space, if you take the theta function and you would like to know how it transforms if you act by gamma, so you act by gamma on tau, and you're also supposed to act on the z somehow. So the map of abelian varieties is not the identity, it's C tau plus D inverse z. This turns out is equal to the determinant of C tau plus D to the power 1/2 times theta of tau z. Okay. So this is a claim I don't really have a chance to prove. It takes quite a bit of work. So, I mean, I could tell you what this is. I could write down a more general formula for the action of any element here. There is in general going to be a very unpleasant 8th root of unity appearing here, which is not here now. But I think this is correct.
What notation is gamma 9, 8?
Gamma 48.
48.
Yeah, so this is, this is just a notation. I mean, it's somehow a very bad style to write a notation which looks complicated and not to explain what it is. But this essentially means that it's supposed to be an element which fixes all points of order 4 and one point of order 8 on the abelian variety, but the structure of that. But there is a finite index subgroup of a certain kind that will not be important for what we do now, such as this holds. Okay. So in particular, if you only care about z equal to 0, and there is a certain exponent of z. Okay, so what I really care about is that if you take theta of gamma t0, then this is the determinant of c tau plus d to the power 1/2 theta of tau 0. Okay. You just set z equal to 0, and there was some exponential here that I forgot to write down, which depended on z, which becomes 1 for this case. Okay. So this seems to be an interesting object then. So definition: a Ziegel modular form of weight k with respect to a subgroup gamma of the symplectic group of the 2GZ is a map f from from the Ziegel upper half space to C, such that for any tau in the Ziegel upper half space and for any gamma in the gamma, we have f of gamma acting upon tau is equal to this determinant c tau plus d to the power k times f of tau. Okay. So this is an analytic definition. Algebraically, this is a section of a line bundle L to the power KL on the quotient here, where L is the bundle of modular forms of weight 1. So, I mean, this is just prescribing how a function on the universal cover of this space transforms if you act by the fundamental group, by the deck group of the universal cover. So if you prescribe that, that means you prescribe the transformation rules for the bundle and the quotient. So in particular, if your subgroup gamma happens to be the entire symplectic group, then it will be a section of a certain bundle on the modular space for abelian varieties. Okay? And slightly generalized on this statement, you can prove, you see that there is a following proposition, which is that for any epsilon delta in 1/2 z over z to the power g, theta epsilon delta of tau at 0 is a modular form of weight 1/2 with respect to the group gamma 4/8 that I never really introduced. Okay. So what this tells you is that these things are all sections of the same bundle on the quotient of the Ziegel upper half space by gamma 4/8. And there is a theorem due to Igusa, Rauch, and Mumford, and the version I state, I think, is due to Igusa. There was very important related work by Rauch and Mumford, which is to say that 1/2 L is very ample on the quotient here, which is to say that the map from this quotient to a projective space of dimension 4 to the g minus 1, sending tau to the set of values of these things, is an embedding. Okay.
What is the corresponding statement for elliptic of G equal 1?
Okay, so for the corresponding statement for elliptic curve, which is what I was going to describe now, is the following. So example, G is equal to 1. So you take tau, right, and you will take theta 0, 0 of tau, which is just a theta function. You'll take theta tau 0, theta 0, 1 half of 0 tau, of tau 0, sorry, theta 1/2 0 of tau 0, and theta 1/2 of tau 0. Right? And the statement is that if you take tau to this set, which you can think of as a point in P3, this determines, so this image determines tau uniquely up to the action of gamma 4/8. So if you know the usual picture for the action of for H modulo SL2Z, this is this picture that I presume you may be familiar with. This is a fundamental domain for the action, so this is third root of 1, this is another third root of 1, and so on, right? And this is the fundamental domain. So the fundamental domain for the action of gamma 4/8 will be a finite cover of this object, which will be mapped into P3 by this. Okay? Of course, you can ask if, so question is, are the values of the theta constants at tau algebraically? So this means we now have the theta image of this thing. So probably makes sense to denote it by AG48. So it's a finite cover of the modular space for abelian varieties, with the quotient being the quotient of, so AG48, which is this quotient, maps to AG, which is the quotient by the symplectic group, right? And that's a finite cover. And this is a subvariety of the projective space of dimension 4 to the G minus 1. Okay, in general. And then, of course, inside here, you'll have the image of MG48. Right? And then one version of the Schottky problem, the classical Schottky problem, is the following. I write down the algebraic relations, the algebraic equations for the theta image of MG48 within the theta image of AG48. Okay. And since I'm running out of time, let me just state one result, and then we'll actually get back to this, and we'll discuss in much more detail what happens in genus 1, which I didn't get a chance to discuss carefully now. So let me just say, let me triumphantly give you the answer to this for genus 4. So you see, for genus up to 3, the moduli space of curves is the same as the moduli of abelian varieties up to taken a closure. And there is a theorem, which is the original work was due to Schottky, Farkas and Rauch did work on this. The formulation that I'll give is due to Egusa. And that's the following formulation. So recall that the dimension of the moduli space of curves of genus 4 is 9, and the dimension of the moduli space of abelian principally polarized abelian varieties of dimension 4 is 10. And of course, if you take finite covers, dimensions don't change. So it's codimension 1. Anything of codimension 1 is a divisor, so it's given by one equation. So I'll write down the equation. So the theorem is the following, that theta of M448 as a subset of theta A4 for it is given by the following equation. 0 is equal to the following. 2 to the fourth, which is also known as 16, I know, but let me write this 2 to the fourth. The sum of all epsilon delta in 1/2 z over z to the fourth, theta epsilon delta tau 0 to the 16th power, minus the sum of theta to the 8th epsilon delta tau 0 over the same thing, quantity squared. This is it. So this is an explicit solution to the classical Schottky problem in genus 4. There is just one equation in terms of the theta constants. So these theta constants are the values of the theta functions at 0, which, if satisfied, guarantees that a four-dimensional complex principally polarized abelian variety is a Jacobian of a curve. And the equation is just this. It's not so long. And there is no combinatorics of characteristics involved and so on and so forth. The original Schottky approach gave some equations that involved a lot of combinatorics. This is Egusa's formulation, and it was proven by Egusa also that this locus given by this equation is irreducible, so it actually gives M4. It was known previously that it has to contain M4. You also notice that I sort of solved the Schottky problem without the level cover, because this equation is invariant under the transformations of the level cover under the deck group, under the quotient of the symplectic group by gamma 4/8. So this is the answer to the Schottky problem in genus 4. And next time I'll discuss why this does not give you so much information for higher genera, and we'll start doing differential equations. But in the beginning, we'll get back and do some examples in low genus to see what happens with theta constants. So that's it for now. Thank you for listening.